You notice? When I sort it up and I also subject the angular motion, when I do that, that means this is what we call unconstrained motion. What is unconstrained motion? That means the motion is not subjected to any boundary condition except just the force. Once again, so besides unconstrained motion, there are also type of motion, which is what we consider, we call it constrained motion. What's constrained motion? Constrained motion is, suppose this is the eraser, but now I will find a way to attach the eraser with some support. So here, the eraser is not or cannot move freely, but instead it's fixed to the point, like this. Now, how is this problem different from the one before? Because the one before, when there's no constraint, the conversion between linear parameters and angular parameters is just like what we talked about before. So before, we never consider any constraint. But when there's a boundary conditions, the constraint provided by the boundary condition, this conversion will not be correct. You will have to consider the combined effect of two terms. And that means what? That means in this case, the center of gravity is right here, but the center of rotation is not at the center of gravity, correct? Because it's being fixed to this point. If you call this point P. That means at a given time instant, you know the angular velocity and angular acceleration. At that time instant, the whole thing is spinning with respect to the point P. And at that instant, you have the linear displacement at the center of gravity, and linear velocity at the center of gravity, and linear acceleration at the center of gravity. The question is, what if I want to know? What if I want to know the linear velocity at maybe another arbitrary point, maybe this point here? Suppose there's a point, another point here. What if I want to know this point I? I want to know what is the displacement, SI, VI, and AI. I give you the linear parameters at the center of gravity, displacement, velocity, acceleration. I also give you the angular velocity and angular acceleration, but I want you to find out the linear displacement, linear velocity, and linear acceleration, not at the center of gravity, not at this support, because at the support, there's no displacement, velocity, acceleration anyway, but any points besides the center of gravity. So this is one type of problem that usually we will consider in planar kinetic equations of motion. The second type of problem is this. Suppose the same problem configuration. And at the beginning, we have angular velocity and angular acceleration. But what if the whole system has been disturbed by some external force? Say there's a moment applying this way. Or trying to think about that there's an object in this kind of motion, but I'm trying to stop the motion. And the way to stop the motion is by either by applying the force or by applying moment, correct? So here, I have all this information provided, but now I'm trying to stop the motion of this problem, not in the unconstrained motion, but in constrained motion. So suppose I have externally applied moment here, and also supply I have the forces I apply here. That means the whole thing is moving in this case, is counterclockwise direction. I want to stop the motion, so I will apply the moment and I also apply the force. The second type of problem is, what is the necessary amount of the moment and the force in order to stop the motion? So that's usually what we are interested in in planar kinetic motion. So here we want to know what is the M or force to be. The third type of problem that we are interested in is this. Suppose there's no external force. It's just by itself. We have things in constraint motion, everything the same. But this time, I want to know that what if I cut the objects into two parts, to this part, and the rest of it. And I want to know that in this kind of constrained planar kinetic motion, what kind of force, internal forces will develop at this interface? In other words, if I cut this one out, and I can divide this into two parts, right? Something like this. The third type of problem is this. You know that internally there must be, in this kind of motion, do you think that there will be internal actions acting at this interface? Anywhere. This is just an arbitrary selection. Do you think that there will be internal normal force here? Do you think it's possible?
Probably.
There must be, right? Just think about what? Think about this. When I'm spinning this, and when I spin it, if I cut this thing in half, do you think that this kind of spinning will actually separate this eraser into two?
Yes.
Of course. So that means what that means. In order to hold this eraser, the two parts into one, there must be internal force holding it together, correct? Remember, this is the general plane motion. It's not just linear motion like this, but it's linear and also angular, put them together. So with that argument, we believe that there must be internal force acting at the interface. And from strength of material, what types of internal forces you can consider? There's normal force, and there's what?
Shear force.
There must be shear force, and also what? Internally. What about moment? Of course, there can be moment too, right? And that's how we're going to consider, in general, at the internal interface, anywhere internally. In order to hold this together, that means the force will have to separate these two together. That means the internal force must be acting like this. Now, the internal force trying to separate this, it must be acting to each other like this. And the shear force will be going, we don't know the direction of shear force, so we just assume positive direction like this. And in terms of the moment, internal moment, of course, the moment goes this way, so we will assume positive moment like this. So the third type of problems we will consider in planar kinetic equations of motion is to ask, what will be these internal forces? Internal forces and moment. The forces we will consider here, of course, the first one is normal force and shear. All right. So that's the purpose why we have to talk about planar kinetic equation of motion. Now the formulation is provided on my notes from page 46 to page 47. So I'm not going to bore you with that mathematical derivation. I will just give you the result from this. So how is this derivation carried out? It's very simple. By considering the force equilibrium, not with respect to this point G, but because in this time it's constraint motion. So you have to consider the moment equilibrium and force equilibrium with respect to the point of constraint. So that's the derivation I did on my notes, page 47. So after that, what's the result? The result is this.
Professor, I have another class in 5 minutes.
Oh, I already went over time. Okay, so I will talk about this. I will finish this one and also example 24 on Monday. All right.
Awesome. Thank you.
I will see you next time.
Thank you.
Sure. Thank you.
Thank you, Professor.
Sure. Thank you, Christy.